A machine learning model can look flawless in the laboratory. It will process thousands of uniform data points with perfect precision, right up until the very moment a single variation is introduced, and the entire system sparks and jams. Achieving 99% accuracy on the specific data used to train a model is a massive red herring. The true objective of machine learning is to accurately predict the future, not to perfectly memorize the past. Because of this, developers evaluate models using a specific metric, the generalization error, also known as the out-of-sample error. Generalization error is the strict mathematical measure of how well a system performs on completely new cases it has never encountered before. To guarantee a low generalization error, we cannot simply write more complex algorithms. We must reorganize the architecture of how we feed data into the machine in the first place. A model's performance on its training data is misleading. The sole proof of its intelligence is its survival in the unpredictable real world. Training a model is an exercise in balance. The algorithm must capture the true underlying trend of a dataset while actively ignoring the random, irrelevant noise surrounding it. This graphic displays 3 distinct line graphs illustrating learning versus memorization. Look at the rightmost scenario, overfitting. The model obsessively memorizes every anomaly, creating a dotted line that wildly contorts to hit every single point. An overfitted model is highly dangerous. It will show a training error of near zero, tricking the developer into thinking it's perfect. But the moment it faces new data, the generalization error will be massive. Conversely, the leftmost scenario shows underfitting. Here, the model is completely failing to capture even the basic structural pattern of the data, drawing a rigid line that ignores the obvious curve. Underfitting usually happens for structural reasons. The raw data is poor quality, the sample size is too small, or receives completely irrelevant features. The center scenario represents our ultimate goal, a robust or good fit model. It threads a smooth parabolic curve right through the middle of the cluster, capturing the true signal while smoothly ignoring the noisy outliers. We cannot mathematically prove which of these 3 curves we have generated just by looking at the training phase. We have to force the model to make predictions on data it has never seen. The first engineering solution to prevent the overfitting trap is simple. We strictly hide a portion of our data from the model during the learning phase. We take our master dataset and fracture it into 2 distinct isolated silos, a training set and a test set. The larger training set usually contains about 80% of the data. This is the only information the algorithm is allowed to look at to build its internal rules and draw its curves. The locked test set vault serves a single purpose. It acts as a simulation of the unpredictable real world. This introduces the unbreakable golden rule of the machine learning pipeline. The test set can only be used once, at the very end of the process, to generate the final evaluation. By physically locking away the testing data, we create an unbiased environment. It is the only way to reveal if our model is truly robust, or if it is just memorizing the training material. But isolating a test set introduces a new operational problem. What happens when we check our model and realize it is heavily overfitted to the training data?
To fix this, developers use regularization. Think of regularization as a mathematical dial, a specific hyperparameter that artificially constrains the model's complexity to force its curves to become smoother. Here is the fatal error most beginners make. They try to find the perfect setting for this regularization dial by repeatedly checking the model's performance against the locked test set. This causes what data scientists call leakage. If you repeatedly tune your algorithm to perform well on the test set, that data is no longer unseen. The test set has indirectly become part of the training process, destroying its value as an unbiased judge. To prevent leakage, we must fracture the training data a second time. This creates a third temporary testing ground called the validation set. This establishes a safe workflow loop. You train the model on the core training data, test it against the validation set, adjust the regularization dial, and repeat until the performance is optimized. In some cases, raw data is too scarce to permanently isolate a chunk of it for a validation set. When that happens, developers use a technique called cross-validation. Cross-validation dynamically rotates many small validation sets through the training process. By repeating the training cycle for each small set, developers can pinpoint a highly accurate hyperparameter value without permanently sacrificing total data volume. Ultimately, this three-tier split creates a sterile laboratory environment. We learn on the training set, we tune on the validation set, and we reserve the test set as the final, uncompromising judge of reality. Yet, even with a mathematically perfect train, validate, and test architecture, a model can still fail catastrophically the moment it is deployed. Consider an engineering team building an iPhone app designed to recognize different species of flowers. To get enough data, the team downloads millions of perfectly framed, high-resolution flower photos from the web for their training and validation sets. But think about the actual deployment environment. The end users aren't uploading professional macro photography. They are taking blurry, poorly lit photos through a low-resolution iPhone camera sensor. This failure point is known as data mismatch. It occurs when the distribution characteristics of the training environment do not align with the messy reality of the test environment. If the validation and test sets are not real, representative samples of the actual use case, your accuracy metrics are a hallucination. The model will break the moment it hits real users. Building a reliable model requires strict adherence to these defenses. Before training even begins, we must ensure high-quality data and actively strip out irrelevant features to prevent underfitting. Then, to prevent overfitting and safely tune the model's complexity, we must physically enforce data isolation. This gives us the unified pipeline required for professional machine learning. Raw data strictly bifurcates into isolated chambers: train to find patterns, validate to constrain complexity, and test to prove generalization. Finally, we confirm the test data perfectly mirrors the gritty deployment reality. Success in machine learning depends on engineering an incorruptible architecture of validation, a system that ruthlessly separates what the machine has memorized from what it has actually learned.